Yes. So since recording has started, yes, that screen is, I hope, is also visible. Okay, fine. So yesterday we have started our discussion on low power VLSI design, right? There we have considered couple of things. For example, first we have, okay, so to design, okay, this any circuit for low power, okay, we should know that what are the ways in by which in any VLSI circuit dissipates power, right? So one of the thing is, or one of the power distribution technique is the switching power. Other one is the, right? So switching power, all these things we have also discussed before, and yesterday also we have discussed. Short circuit power distribution you also know, static power distribution also you know. And regarding the in our discussion towards this switching power dissipation, we have seen this that it is given by this alpha into CL VDD square into F, right? So here the important thing is this power you can see is proportional to VDD square, right? So this VDD plays a major role in determining the power dissipation. So if you have to reduce the power dissipation, right, or if you have to design a low power circuit, then obviously the VDD you have to reduce. But there, you cannot really do that thing without hampering the other performance. So what is the other performance? For example, you can see here, this is the supply voltage and here normalized delay, this axis, and this axis we have plotting the normalized power dissipation. So you can see the power distribution decreases as you reduce the power supply or supply voltage, but at the same time there is a penalty in terms of the normalized delay, because the driving the capability of that transistor or this any gate reduces as you reduce this VDD, right? So as a result you cannot really drastically reduce this VDD without affecting its performance. So there we have talked about couple of things. We have talked about like maybe then we could have lowered the threshold voltage, because ultimately this power, if the transistor is in saturation, it is VGS minus VTH squared. So which is basically ID is proportional to VDD minus VTH squared, right? So as you can see, you can reduce it, you are reducing this VDD, but at the same time if you can reduce this threshold voltage also, then probably you can keep this ID towards or maintain the level of ID. But here is also a constraint, the scale by which you can reduce this VDD, you cannot reduce this threshold voltage using in the same scale, because it creates lots of other issues. For example, the leakage current issues, subthreshold conduction issues, and all these things, right? So there we have considered this thing that can we do some purpose or can we make some arrangement such that when the device is operating, we will reduce, okay, when the device is active, we will make the threshold voltage low. Okay, when the device is asleep or standby, then we should make the threshold voltage high to reduce the leakage current or the static power dissipation, right? So one of the arrangement is this variable threshold voltage CMOS, right? This was the circuit that we have discussed yesterday. So here is the substrate or bias which control the substrate bias control circuit which controls the substrate bias. So by controlling the substrate bias, if it is in sleep, if it is in the sleep condition or the standby condition, you make the threshold voltage higher for both PMOS and NMOS. If it is in the active mode, then you make the threshold voltage lower, right? So this is one of the technique. The next technique is this one, multi-threshold voltage CMOS. So here we do not change the threshold voltage in a depending on whether it is sleep or in active condition, but rather we use two fixed transistors, two types of transistors. One type of transistors are having this high threshold voltage, and the other type of transistor, these two are high threshold voltage, and other transistor which will implement the logic operation, we will keep that inside and make that and keep the threshold voltage of this with low, okay, as low as possible. And here we have also mentioned we have also commented on the width of these two transistors, because we want the on resistance of these two devices should be as low as possible. As a result, you have to make this width quite large, right? So that the voltage drop across these two should not be that drastic. Right, so this is the next technique that we have discussed yesterday. Third one that we have discussed is the technology mapping, right? They are just to discuss the technology mapping. Here basically we are not focusing on VDD anymore, but we are focusing on this alpha or this switching activity parameters, right? So here, how do you find this switching activity or how do you determine the switching activity? For that, we should know this, like what is the transition probability from 0 to 1 of this output, right? Because the power is only distributed when there is a transition from 0 to 1. So how do you find it? We find it, we have considered this PA, PB. PA is the probability that the input is 1, PB probability that this input B is 1, and PF is the probability that this output is 1. Then for this gate, AND gate, this probability of output being 1 can be given by the probability. When both the inputs are 1, then only the output will be 1. Similarly, for other gates also we have seen. For example, OR gate, it would be like this, right? Okay. So if we can now define switching activity or switching or this transition activity by this, then we have considered also one example. For example, this 4 input AND gate. So we know that we cannot design multi input AND gates. It is not good actually from circuit design point of view. So we have split it into 2 input AND gates. So we can see one design is like this, other design is like this. And if the PA, PB values are like this that we have considered yesterday, then we have seen the total switching activity for this is this one and for this is this one, right? So basically we are implementing the same thing but based on this design. So you can see the switching activity of these two designs are so different. Yeah, please come. Right. So the fourth one that we have discussed is called the input ordering. So what do you mean by input ordering? So here you can see the inputs are A and B. Here is input is C. So what is this Z? Z is basically A, B, C. So here also, but here we have taken B, C here, A here. Right. As a result, the Z is this A, B, and C. So both are implementing the same function, right? But if you now suppose PA, PB, PC values are given, then you calculate the total alpha. You get the total alpha here like this one, and here you get the total alpha like this. So you can see here the for highly active, right? Which one is high active? High active is this PA value. Just shift this PA value to the next one here, right? And that will drastically reduce this total value of alpha. So this is the input ordering. Okay, now if you have understood, okay, this is a brief review of yesterday's class. So if you have understood this class up to this much, then please tell me or comment on what will be the, yeah, please come. Power dissipation in dynamic CMOS logic. Okay, can you comment? Power dissipation in dynamic CMOS logic based on whatever we have discussed. We have already discussed dynamic CMOS logic to a quite great extent, right? So please do comment on it. So please, can you make any comment on this? Power dissipation in dynamic CMOS logic. So dynamic CMOS logic block diagram, if you recall, it's like this, right? It's clock. Here it is V in, right? So this is the function that you are going to implement, and you will keep the function here, right? It is not like the type of multi-threshold logic design where this transistor have different threshold and this transistor have different threshold. Not like that. All transistors have the same threshold voltage, right? And here,
dynamic CMOS we only needed pull down network.
Sorry.
In dynamic CMOS,
we
only needed pull down network.
Yeah, in dynamic CMOS, we only
needed pull down network.
Oh, sorry. Right. True. Right. Very good. Yeah. So here, suppose I want to make an inverter. Then what should we add? Only this NMOS. Right. Very good. Okay. and here is this output, CL, right? Okay. So here when this clock is 0, so here you know there are two stages. One is this pre-charge state, next one is the evolution stage. So in pre-charge state, clock is equal to 0. So when you make clock equal to 0, what will happen? This capacitor will charge. Okay, and when you make evolution state, then depending on that it will discharge. But during discharge, see, if there is a power consumption will only happen during the charging only, not during the discharging. Discharging half of the power will be dissipated, right? But that power is not being consumed from the VDD at that point, right? That power will be only consumed when? Power will be only consumed during the charging phase. Okay. Now consider this clock equal to 0. This is say this V out equal to 0. Then there will be a charging. Right? Very good. But say in a previous state, right, the output was equal to VDD. Will there be any charging? No. Right? So that means if now the output is equal to 0, then in the next stage there will be power dissipation, right? So if if at the present state the output is equal to VDD, then in the next state there will be no power dissipation. So depending on that, what can you say? There will be only power dissipation if the output is equal to 0. It does not matter. So if the present output is equal to 0, then only there will be a power dissipation. Right? It does not matter whether the previous one there was a 0 or 1. Does it matter? It does not, right? If now it is 0, there will be power dissipation. Right? So then, unlike the static CMOS, here the power dissipation does not depend on the transition, that whether the output is transitioning from 0 to 1 or 1 to 0, not like that. Here the power dissipation occurs depending on the transition probability, but on the probability of the signal probability of having it to be equal to 0, right? So that means, can we then say that the power consumption in dynamic CMOS is determined by the signal value probability of the output node, not by the transition probability or switching activity. So let us write this point. This is a bit important.
By the term switching activity, you always mean the switching activity at V in, right?
Yeah. Could you please repeat your question? Here the audio is not very good actually. Could you please say it again?
So by the term switching activity, you always mean the switching activity at V in.
Are you getting right? Okay, maybe I understand. There is one more thing I have to do. That is, I have to keep my mobile and use that mobile and one headphone in my ear. Actually, here the audio is not good. I'm not able to hear it clearly. So yeah, could you please try typing that one? I'm sorry for the inconvenience, but I really cannot understand. Yeah, it would be great if you can type it. Yeah, could you please check if there is any? Yeah, in the chat something is coming. Switching activity for V in. Okay, so no. Here we are not, see, the switching activity. So, is my net is working? Yeah, net is working. Yeah, yes, can you still hear me?
Yes, sir.
Hello, those who are online, can you still hear me?
Yes, sir, we can hear you.
Hello, can you hear me? That means this is not working. Huh? Oh, current এটা কাজ করবে না? কি করব? হ্যাঁ। Oh, you can hear. Actually, there is a power cut. Okay. So if you can hear me, great. Then we let us continue. Okay, you have written. Is the okay? So yes, Shubhayun, you have written in the chat window. Do you mean the switching activity for this V in and the next? If there is no clock, then V out will change according to V in. No, Shubhayun. What I am saying is that here we are, for the time being, do not consider the switching activity. Okay, we are just considering when the power will be consumed in dynamic circuit. So in dynamic circuit, power will be consumed only when consumed when this output is equal to 0, because in the next step then this node has to be charged, right? So if here, suppose it, okay, what I am trying to say, please try to think about it. Say you have this capacitor here, this capacitor CL, and this is VDD, this is ground. Okay, right. So this is clock, this is clock. Okay, so here you have given 0, 0, and say here it was initially 0. Now then it would be charged. Okay, now then it would be charged. It does not matter during evolution state what would be the value of this. Okay, whether this would be V in would be 1 or 0. Okay, V in would be 1 or 0. It does not matter. You understand my point? So what it matters is that whether this value is now 0 or 1. If it is 0, then only there is a possibility during pre-charge it will be charged. If it is 1, okay, then it is already 1. Then that there will be no power dissipation.